In this video, we're going to talk about the derivative function, all right? Remember that we've already talked about the derivative at a point. Remember, the derivative at a point was considered the instantaneous rate of change. We also said that the derivative at a point was the slope of the tangent line to the graph at that point, right? Instantaneous rate of change, the slope of that curve, the slope of that tangent line. Remember, the difference between the tangent line and the secant line is that the tangent line touches your curve at one point of interest, and a secant line intersects your curve at two specific points on an interval that you're interested in. All right. Well, what we're going to do now is, instead of talking about the derivative at a point, we want to talk about the derivative as a function. All right. And so the derivative function, it says for a function f, we define the derivative function f prime, and what you'll usually see it written as is something like f, excuse me for a second, something like f prime of x, if x is our input value, or we might say f prime of t. We use functions like revenue and cost, so we might say r prime of q, right? It's not going to be at a specific number anymore. It's going to be at your variable, your input variable. That's what we mean by the derivative function. So there we see the f prime of x. It's the instantaneous rate of change of your function f, but at all of your x values for which your function and its derivative is defined. All right. And so what we're going to do is we're going to kind of just get conceptually some relationships between the graph of a function and the graph of its derivative, and we want to know those relationships very well. I have a graph of a function here. It's a function because each input gets assigned to one output, but I have 5 points here, and I basically want to find an estimate for the derivative evaluated at each of these points here. Because remember, your derivative function is your derivative of your, at all the points where your function is defined. So if I pick some points, find a derivative, I could use those the values of your derivative at those points to help come up with the graph of the derivative function. And that's what we're doing here in this example. So f prime of 0. So we're going to write down some stuff here. You don't necessarily have to always write this stuff down, but f prime of 0 basically equals, I'm going to write this out in words. I'm going to type this on a computer. It is basically the slope of the tangent line, if I can type, of f of x at x equals 0. That is what your derivative function is. It's the slope of your tangent line to your function at x equals 0. All right. And so what I'm going to do is to find an estimate there is I'm going to try to draw a tangent line. Now, I'm going to try to draw it using this computer here. Tangent line just touches your graph. It's going to be harder than I thought. All right, it just touches your graph of your function at that point, right? So if I drew a tangent line, it would look something like that. And so what I'm going to do is I'm going to try to find the slope of that line, because that is what my derivative f prime of 0 is going to equal, right? And so I've drawn that tangent line. I want to find the slope. Well, it goes to the point, or touches your graph at that point, and I'm going to use rise over run, right? Because slope is always rise over run. Well, okay, I'm going to get a little smart here. This is a grid. So I know if I go to the right, I'm going to have 1. So I'm going to write my slope so that my run is always 1. All right. I'm going to go up. In order for me to go 1 unit to the right, or 1 running unit to the right, I got to get to that point right there. So I go up about 1.5. Right. So I go up 1.5, and I go to the right 1 unit. So 1.5 divided by 1 is 1.5. So f prime of 0 is approximately equal to 1.5, right? It's the slope of your tangent line, right? So I'm going to do that for f prime of 1, right? I'm just going to write it down, and I'm actually going to do this one in a different color so that our graph won't get so messy. Let's do blue here. I'm going to try to draw me a tangent line, and this is going to be a little difficult for me. because I want a line that just touches but doesn't cross my graph at that point. And I want to make it long enough so that I can actually calculate the slope. So here, f prime of 1 is going to be the slope of my tangent line. I'm going to at x equals 1. And if I look at this point is about 1, a little over 1, and this is a little over 2, right? So I go up about 1 unit, and I go to the right about 1 unit. I get 1 over 1, and so that is going to be 1. All right. Let's do another one. F prime of 2, right? It's going to be my slope of my tangent line at x equals 2. So I'm going to go to x equals 2, which is this point here. I'm going to draw me a tangent line. All right. I think this is a good enough tangent line. Actually, I think that's a bad tangent line. I wanted to touch this point here, the black point. My blue point is almost on it. So this looks about right. This point is right above 2, right? So if I use my rise over my run, I hope you guys are seeing what I'm doing. Even with colors, it's still kind of messy. But it looks like I go up about a half of a unit and then to the right 1 unit, and I'm back on that line. So I'm going to say I go up about 0.5 and I go to the right 1 unit, and I get back that equals about 0.5. So my derivative at x equals 2 is about 0.5. Now, what's nice about x equals 3, in order for me to find an estimate for f prime of 3, that's the slope of my tangent line at x equals 3. This is approximately, all right, what I'm going to do is going to try to draw my tangent line. And what do you know? If I drew a line that just touched it but didn't cross it, it looked like it'd be perfectly horizontal. And when you have a horizontal line, the slope is 0, right? And so my rise would be 0 because it's completely horizontal. I can still use that run of 1. And so that is 0 units. And then last but not least, we're going to do f prime of 4. And I'm going to go back to red here. All right, remember, your derivative at a point is your slope of your tangent line. At x equals 4. I'm going to approximate that using a rise over a run. I'm going to try to draw my tangent line. Looks something like that. It just touches the curve but doesn't cross at that point. And now if I do my rise over run, I'm going to end up going left. And I'm going to make sure that I get to that. I want 1 unit. So I'd go up about 1 1/4, and I go to the left 1 unit. So 1 1/4 is 5/4, and my run is 1. So that's about 1.2. My run is to the left 1, so that's the negative. So that'd be a negative 1.25. All right. These are estimates. Yours may be a little different because we're drawing tangent lines. It's a little subjective here, but in general, they should be close to those values there, right? And so basically what we've done is we have some input values where our derivative function is defined and some corresponding output values, right? When you input 0, you get an output of 1.5. When you input 1, we get an output of 1. When you input 2 into your derivative function, you get an output of 0.5. This is a function. And basically what we've just done is we've created some ordered pairs. It's almost like back in the day when you created graphs and you wanted to plot some points, you choose some x values like 0, 1, 2, 3, and 4, and then you plug it into your function and you get output values. When we plugged in 0, we got 1.5. We plugged in 1, we got 1. We plugged in 2, we got 0.5. We plugged in 3, we got 0. We plugged in 4, we got negative 1.25, right? And so that's what we did. The only difference here is that this function that we plugged it into is actually our derivative function because the derivative is the same thing as the slope of the tangent line. So this is x, and that's f prime of x. And so basically we have a bunch of ordered pairs. That's the 0.0, 1.5, the 0.11, the 0.2, 0.5, the 0.30, and then the zero point 0.4, negative 1.25. And so I can plot these points, and since this is f prime, I can graph my derivative function, all right? So I'm going to plot these points. I have the 0.0, 1.5, the 0.11, the 0.2, 0.5, right, 2 and up 0.5, the 0.30, and then the 0.4, negative 1.25. And so I get a graph that's a little curvy, and it looks something like that, all right? And so this is our derivative function. So we went from a curvy function that looked like this to a derivative function that looks like this. There are some things that we want to notice. Our function here, and I'm going to draw it over in black, looked like this. And I want to connect the behavior of that function to our derivative function, right? For instance, on this part of my graph that's in yellow, my regular function was doing what? One of the things that it was doing was it was increasing. That's really hard to see, I'm sorry. That part of my function is increasing, right? When that part of my function is increasing, my derivative, notice my derivative is decreasing, but notice the sign of my derivative. So from 0 to x equals 0 to x equals 3, this function was increasing, and this part of my function was positive. So we kind of already talked about this before, but when my function is increasing, your tangent line is going to have a positive slope, right? That means your derivative is going to be positive. That's one of the relationships that we want to know. Another thing, on this side of my graph, my function is decreasing. What do you notice about my derivative? So it's decreasing from 3 to 4, right? Notice my function is below my derivative function is below the x-axis. That means it's negative, all right? And so that's two properties that you want to know, right? F prime of x is greater than 0 when f of x is increasing. So your derivative is positive when your function is increasing, and your derivative is negative when your function is decreasing. The derivative equals 0, well, the only point where our derivative was 0 was this point right here, where x was equal to 3. We had a horizontal tangent line, and actually, at that point, it's neither increasing nor decreasing. Okay? In fact, your derivative changes signs from positive or negative, or from negative to positive at points where f of x changes from increasing to decreasing, or vice versa, decreasing to increasing. And that is exactly what happens at x equals positive 3 here. Our derivative is changing from positive to negative when our function is changing from increasing to decreasing. Had our function have been going this way right here at x equals 3, sorry, make sure this is the minimum, then our function would still have a horizontal tangent line, and we'd also be changing from decreasing to increasing in the same manner. Our derivative would be 0. All right, and so these are the relationships between the function and the derivative that we want you to know. Let's look at some graphs and use this information. It says draw a function with the given information about this derivative. All right, the derivative is greater than 0 or positive for x values greater than 0. The derivative equals 0 at x equals 4, and the derivative is negative or less than 0 for x values less than 4, right? What I like to do is I like to translate that to a number line, right? Some important values that are going to be on that number line are related to x, and that's the number 4. All right, this, I'm going to label this as f prime, right? So basically what it's saying is that my derivative is greater than 0 or positive when x is greater than 4. Numbers greater than 4 are to the right of 4. So I'm going to put a plus sign that represents positive. I'm going to skip over this one here, and I'm going to go to the last characteristic. It's less than 0 or negative for x value is less than 4. I'm going to put a negative sign. And it equals 0 at x equals 4. That means we have a horizontal tangent line. Well, I'm not there yet, quite there yet. I'll put a 0 there at x equals 4. All right, your derivative is neither positive nor negative, it's 0. Now, each of these things translates to something about your function, right? So I'm going to do another number line, and this number line is going to be reflective of these values here, but since I'm going to draw the function, I'm going to put this number line under here so that it can help me graph. All right, and the important number on this number line is the number 4, and I'm going to line it up with the 4 on my graph here. And this is going to be some information about my function. Notice I labeled this number line with an F instead of an F prime. This was the derivative. This is the information that my derivative tells me about my function. When my derivative is negative, with like in this case right here, my function should be decreasing. So I'm going to put a DEC. When my derivative equals 0, my function has a horizontal tangent line. It changes from increasing to decreasing or from increasing to decreasing. Or it's neither increasing nor decreasing. All right, that's another way to say that. And then when my derivative is positive, which is for x values greater than 0, my function is increasing. Okay. Now, I only know this information. I don't know what specific values my functions carry. My function actually passes through. And so what I'm going to do is I'm going to draw a graph of a function that's decreasing until I get to x equals 4, has a horizontal tangent line at x equals 4, and then it starts to increase or go up. Now, since x equals 4 is an important point, and I know I'm going to have to decrease until I get to that point, I'm going to pick any point on my graph with an x coordinate of 4. It does not specify. And I'm going to draw a graph that's decreasing until I get there. And then after x equals 4, it's going to change to increasing. And so this is a graph, a potential graph of y equals f of x. It satisfies those characteristics. All right. Now, let's go in the other direction. It says use the graph of f of x to graph f prime of x. All right. Now, what we could do, all right, I'm going to go back to the beginning. We could try to do what we did here. All right. Now, I'm not going to do that. That takes too much time. And this, I would have to use so many points in order to help me do this. All right. For this graph here. Sorry. And so what I'm going to do is I'm just going to look at the increasing, decreasing, and horizontal tangent line behavior of this graph in order to tell me where my derivative is going to be positive, negative, or 0, right? And I should have specified the computer software that I use to do these graphs don't have endpoints. So if I don't arrows, so if I don't put endpoints there, it's understood to be arrows. On a test or a quiz, I'll always be specific. All right. What I want to do here is I'm looking at y equals f of x, right? So this graph is y equals f of x, and I want to graph f prime over here, right? The derivative. So remember the relationship between the function and its derivative. When the function is increasing, when the function is decreasing, when the function is neither increasing nor decreasing, that's horizontal tangent line language, okay? Then it tells us that the derivative is positive, negative, or 0, right? It's just telling us the sign of the derivative. So I'm starting with f of x. So since I have a graph like this, I'm going to do this on my number line. I like to look at where we have a horizontal tangent line, right? Those are going to be very important points, right? So notice I have a horizontal tangent line at this point where x equals -1. So that's going to be a point, and at x equals 2. I know I have a horizontal tangent line there. I have a horizontal tangent line there, right? Before I get to x equals 2, my function is increasing. So I'm going to put an INC here. It's also increasing for x values that are greater than 2, which is this part of my graph here. So I'm going to put an INC here. Between -1 and x equals 2, my function is decreasing. So I'm going to put a DEC. So since this is my function line, that's f, and I want to know what's happening to my derivative, or I want to graph my derivative f prime, let's translate that on this number line here. Now, that -1 is still important. That 2 is still important. At those values, I know that my derivative is 0. So that means that my derivative is 0. That means my functional value at my derivative is 0. Well, when my functional value is 0, that means that's the y coordinate. That means my graph crosses my x-axis at those points. All right. So those are points that I know for a fact are the point, right? Now I'm going to go to this interval from -infinity to -1, right? My function is increasing. Well, when the function is increasing, the derivative is positive. That means the y values are positive. Positive y values are above your y-axis. So it's positive on here, and since it's increasing for x values greater than 2, it's positive here. When it's decreasing, your derivative is negative. So since it's decreasing between -1 and 2, I know I have a negative sign here. So this has to do with y values, right? I don't know the specific y values. I'd have to find the slope of the tangent line of all of these points to get a good idea of what y values I should use. We're not going to do that. I'm just going to sketch the graph of your derivative. I just want to make sure that it has the behavior. The only points that you know for a fact that your derivative has is where it has those horizontal tangent lines. Where your function has your horizontal tangent lines, your derivative equals 0, and a function that equals 0 crosses the x-axis at that value. Okay. So these 2 points, let me draw this in black, are set in stone. Everybody should get these same 2 points. All right. Now the difference is, okay, well, I got to draw a function that's positive. That means above the x-axis. So positive. It gets to 0 at x equals 1, and between 1 to 2, it becomes negative, but at 2, it has to go back through this point at 0. So it's going to go down and be negative, but it's going to have to come back up and be positive, right? And then after 2, it becomes positive. And so I get a graph that looks something like that. All right. And there we go. Is this the same graph? No, this is slightly different. Again, we're going to look at this example where now we're going to look at we're given the graph of the derivative, and now we want to draw the graph of the function. So remember the relationship. When I'm looking at the derivative, whether the derivative is positive, 0, or negative is going to tell me whether the function is increasing, decreasing, or neither increasing nor decreasing. And so when I'm giving graphs like this, again, I like to draw me a number line. And notice here, I'm looking at f prime. Now I'm looking at whether f prime is positive, 0, or negative, above the x-axis, on the x-axis, or below the x-axis, right? So the points where it crosses the x-axis are very important points. That's where your derivative equals 0. So this point right here is important, this point right here is important, and this point right here is important. So I'm going to put those numbers on my number line. I know my derivative equals 0 at those points. I'm looking at the sign. I'm not looking at increasing or decreasing here. Not yet. I'm looking at the sign of the derivative, okay? My derivative is positive here. So I'm going to put a plus sign. It's positive on this interval from 1 to 3. So I'm going to put a plus sign. My derivative is negative for these values here. So I'm going to put a negative sign, and it's negative on this part of my graph here as well. So I'm going to put a minus sign. Now that I know that about my derivative, it's going to tell me some information about my function f. So I'm going to use those same x values, -4, 1, and 3. Wherever I had 0, I'm going to have a horizontal tangent line, horizontal tangent line, horizontal tangent line, right? When my derivative is positive, my function should be increasing. So I'm going to put an INC here and an INC here. Where my derivative is negative, my function should be decreasing. So I'm going to have a DEC and a DEC. right? And so what we're going to have here is my function is going to be increasing until I get to a horizontal tangent line at -4. So I'm going to pick a point that I can go up to because it's going to increase until I get to -4. I'm going to pick a point. You don't have to pick the exact same point. Your point can be up here. Your point can be down here, okay? Then it's going to decrease until it gets to x equals 1. X equals 1 is here. I'm going to pick any point. Now, I would never pick a point this high because I wouldn't be decreasing, right? And I need my function to decrease after it leaves this point here. So don't pick a point higher than this point. Any point lower than this point will probably work. All right. Then it's going to increase after up until we get to 3. So I'm going to choose a point that's higher than that point so I can actually increase. And then my function is going to start to decrease indefinitely. And so I'm going to draw a graph that's increasing. Horizontal tangent line, so it's going to turn around, decrease, horizontal tangent line, and then we're done. That is a graph of our function, y equals f of x. Now yours may have looked, I'm going to show you this, yours may look like this. Both of those are acceptable to me. All right, I'm not concerned about the actual points. All right, as long as your behaviors are exactly the same. So I need to see a horizontal tangent line here, here, and here. Notice this graph has the horizontal tangent lines there as well. And I just need to see increasing, decreasing, increasing, decreasing. And always draw a smooth curve. We don't want any, derivatives aren't defined at like areas where you may have a corner or a cusp or something like that. So we don't want anything to be straight or like sharp, any sharp edges. Derivatives require smooth curves. That's why we look at exponential functions, logarithmic functions, and polynomial and power functions in this course. All right, when we use other types of functions, we run into some errors. All right, so that is that. So know the relationships between your function and the derivative so that if I give you the derivative, you can draw the function or sketch the graph of a function. If I give you a function, you can sketch the graph of the derivative. And if I give you some properties of your derivative, you'll be able to sketch the function. All right. Last but not least, we're going to just review estimating the derivative numerically. This is something that we've already done before. This is the derivative at a point. Remember, your derivative at a point is basically you use your average rate of change function in order to help you get a good estimate of your instantaneous rate of change, right? And so if I want to find f prime of a, I just use my f of b minus f of a all over b minus a. But remember, this has to be a small interval, right? Small interval. Okay? So it says assuming x equals a and x equals b are close together. And so remember when we were doing the derivative, we would say, oh, if I want to find f prime of 0.2, well, I could use f of 0.2001 minus f of 0.2 all over 0.2001 minus 0.2, right? That would be a good estimate to help you find your derivative at f of at 0.2, right? Well, when you're given a table of values, you're restricted to that table of values, right? And so this is just reiterating. We want to use this. We'll still have to use this formula here when we're calculating the derivative, right? So if I want to find f prime of 0.2, that's a prime, one prime, 0.2. I can do f of 0.3 minus f of 0.2 all over 0.3 minus 0.2, right? And so f of 0.3 is 7.5, f of 2 is 8.2, all over 0.1. And I actually have to do that calculation, these. And I get -7. So that equals -7. Notice I use a value to the right? So this is your right-sided derivative. We can also calculate this derivative using the 0.2 and the 0.1. So we can get another estimate of the derivative by doing f of 0.2 minus f of 0.1 all over 0.2 minus 0.1. That's a 1. So I have an 8.2 minus a 9.1 all over 0.2 minus 0.1, which is 0.1. And that will give me a negative 9. And then again, okay, and so this is a left-sided derivative because I use 2 and a number smaller than it. And then I can calculate f prime of 0.2 using f of 0.3 minus f of 0.1 all over 0.3 minus 0.1. And when I do that, I have a 7.5 minus a 9.1 all over a 0.2. And I get a negative 8. And this is a two-sided derivative. And if you notice here, if I do the average, which is add up the two things and divide by 2, you get that same. So if I do the average of the negative 7, which is your right-handed derivative, and your left-handed derivative, which is negative 9, do the average of those, and you'll get the two-sided derivative. So you'll never have to really go through this last step here. If you did the left and the right, just take the average of those two, and you'll always get the two-sided derivative. All right. So this is all for this video. Definitely know the relationship. This was just a review. This page right here is sort of a review. But all of the other stuff is the new content that I want you to get very comfortable with, knowing the relationship between the function and the derivative. I'll see you in the next video.